Hello, good evening. This is Baji, and this is Baji's mother, me. On Baji the Handsome Cat, we are live. We have gone live. We welcome you to our live stream. Thank you so much for joining if you're joining, and thank you so much for watching. If you're watching this as a video upload later on, we started our live today a little bit late. I wanted to go live earlier around 9 p.m. or 10 p.m. Eastern Standard Time, but here we are. Baji and Fuji and Suji, we're all joining you. We've had our snackies and our din-dins, and we got our waters. And hi, Clicker, back. Yes, we got our waters. We took out the trash. We did our walk. Kitty cats had their zoomies. And actually, we were playing together just a minute ago. I was on the phone with my friend. And so this is why we're late at the moment. But then my friend is watching a different live stream. So I was like, okay, I gotta go live now. Hi. Clicker says, it's been a long time since I went in your lives. Yes, it has. I have been going live on most days. I did take a little bit of a break last weekend, I think. What day is it today? Sunday? So last weekend, Saturday, Sunday, I was traveling. And then I was back on Monday late night. And then I think I missed maybe... I can't remember if I went live on Tuesday or not, but I might have needed a day. So that's the only break I've taken for a few months now with these lives. But we are back. We're pretty much going live on most days, pretty much every day. So if you can catch our live stream, that would be amazing. We actually have been talking a lot about various physics topics. Lately, in the last few lives, we've been covering cosmology. So if you're joining, thank you so much for joining. I will be... Oh, you know what? I completely forgot to get my laptop. Hi, Melly. Hi, Melly G. How are you? I completely forgot to get my tablet so that I can share the live from my other device. Hi, Melly. How are you? So actually, let me go get my laptop right now and share the live. I'm good. How are you? I'm good. Thank you for being here. Can you guys still see Baji? Ooh, actually, maybe you can look at Suji Mama for a second. I'm going to go get my laptop. Hi. So we have been going live a lot, but yes. Oh, looks like my cat. Oh, good. Melly says, hi, I'm good. How are you? Nice kitty. Braden says, Newborn says, oh, looks like my cat. Abraham Pant GA says, what cat breed is it? These kitty cats are all domestic short hair, but I imagine probably mixed with other things. Baji here is extremely genteel with blue eyes. Could be some ragdoll in there. Zias family 2 says I. Hi Zias. Hi Paul Abyss. How are you? How are you doing? Thank you everybody for joining the kitty cat live. I want to pet the kitty, says Mr. Rogers. How are you, Mr. Rogers? How are you, Paul, Zias, Abraham, Braden, Melly, Clicker? Zias, Abraham. There you go. Listen to my voice twice. I am trying to share the live from my other device here. So thank you so much once more for joining. Melly G says, it grips like the special ed student holding the pet hamster. Oh, I don't know what that is, but okay. Is that a piece of content that you watch? I'm going to tell my friends and community that we have gone live. Oh, maybe you're talking about Baji's. Hi! Hi, Suji Fuji. Hi, baby. Little kissy. Oh, they want snacks. They just got it. They just got snacks. Oh. Okay. Okay, Melly. That's weird. But thank you for being in the live. Goodness gracious me. Sometimes I go into a little bit of a shock upon reading your messages, but thank you all the same. Hello. Hi, Suji. Hi, Suji Mama. Hi, baby. So anyways, thank you guys for joining. Melly says sorry. Okay. Yeah. Thank you for joining. The boys love me. Okay. Well, there are some kitty cat boys here. So, anywho, once again, welcome to the chat. Welcome to the live. Let me put this right here for a second. You seem so nice. I am nice, yes. I will probably be talking about physics soon, Melly. I do hope that you'll stay for that. Most welcome to stay for that. So, yes, here's the kitty cats. They look at that. Baji is going to check the his automatic cat toilet. I got my degree in EE. Oh, wow. Electrical engineering. Oh, that's awesome. Very nice. What do you do now, Melly? Fuji. No, Fuji. Garnish, no. No, baby. Oh, look at this. Look at these babies. Look at these babloos. Nothing related to EE, lol. I do software development. Oh, good. But I took calculus-based physics 1 and 2 and modern physics. Oh, nice. We will talk about physics. Thank you guys, everybody. Appreciate if you could share the live and like the live, please. Thank you. Hi, Eli. What the Sigma? Hi, Eli Leluin. How are you? Hi, join us and chat. We will get started. No, Fuji. Fuji, please don't break the auto feeder. Fuji, no. Okay, so if you like Maxwell's equations, we can certainly talk about electromagnetism. We actually had a number of lives. Hi, Baji. Are you gonna monitor the AI cat toilet, or are you gonna come join us? Sometimes Baji gets very preoccupied with his automatic cat toilet, which he's the brand ambassador for. Hi. And then these guys, they want snack time whenever I get up. So there is that. I can tell by your voice. Okay. Thank you. People do like my voice. So Melly and everybody else, we have been covering a bunch of physics topics on the lives, especially the nighttime lives. We actually already see lots of books here. You might like this one, Melly. This is Introduction to Electrodynamics, by Griffiths. Very common, very well-known book for electromagnetism type of topics. I don't know how much we will get into it tonight, but I'll show it to you. This is the book that we used for undergraduate E&M, electromagnetism for physics majors. But lately, we have been talking about cosmology. We actually, so if you're interested in our previous lives, we have talked about, so the time right now is close to, oh, here it is. It's 12:10 in the morning on Monday. So in the past live streams, probably like something like a few live streams ago, until a few live streams ago. So if you later on stay in the live now, but if you subscribe to the channel and then go find my live tab on the channel, if you go and maybe go back like a few live streams ago, we actually covered all the topics from this book called Einstein's Cosmos by Michio Kaku. And we at length talked about electromagnetism, Maxwell's equations, Einstein's contributions, special relativity, relative nature of space-time, energy mass equivalence, all of that we covered at length. And it was very interesting discussions, very engaged audiences talking about all of that. So if you're interested, you can go catch that later on. But then lately, basically what I was doing was referencing this book right here as a way to cover 20th century physics. So someone mentioned modern physics. A lot of the time when people talk about modern physics, what is modern physics? They actually mean the 20th century physics. They don't necessarily mean the extra like current physics. Like pretty much the stuff that's happened in the last couple decades of the 20th century, like the 1900s. So in the 1980s, 1990s, up to now, is sort of more of the current physics and the progresses that we're making now, such as trying to figure out what is dark matter, what is dark energy. Those are sort of the current efforts. But sometimes when the courses are taught and they say modern physics, really what they mean is more of the, relativity. Since Einstein developed, he published about special relativity in 1905, and then he worked on general theory of relativity as well in the 1900s. By the time it's 1920s, he's already contributed a lot of this. Pretty much relativity is a thing at that point. So pretty much modern physics usually will mean relativity and the developments in quantum mechanics, which also happened in parallel during that same time. So we covered a lot of that and what I call 20th century physics, because it lays the foundation for a lot of the things that we would cover now and what is currently happening in physics. So I thought it was a wonderful way to get it going, and we use this book a lot for that purpose. Then we have kind of moved into more, a little bit more recent topics. I'm still kind of referencing books and textbooks, so not necessarily getting into like journal topics or papers too much, because some of the topics that are still developing and the research still happening, do you think space is actually a void? Some people think that there is a very small layer of something that we can't see yet. Yeah, I think you mean maybe the extra dimension stuff that people have thought about. That could be what you mean. Yes, for sure. I'm open to sort of understanding that. I don't know exactly, because we live mainly in 3 dimensions, spatially, and then the time dimension. So because we mainly live in 4 dimensions, including time, some people have actually thought that there are other dimensions. They could be small, but we just don't experience them. And that could be the reason for certain things. That could be why we don't know, for example, what is dark matter, and maybe Einstein's equations could be solved more exactly if you included higher dimensions. And work like that actually went into basically laying the foundation for string theory and superstring theory. So these are the types of things that we kind of discussed when we referenced this book earlier in our previous live stream. So we kind of covered this already. So what I've been doing moving forward is I talked about, I referenced a few topics from an astrophysics book, and particularly we talked about dark matter candidates. So now when we come to the 21st century, pretty much I'll, mention it again, which is that basically the biggest open questions right now are what is dark energy, what is dark matter, and what is the origin of all the elements. Granted, we know the processes in which a lot of the elements are made, but there are certain elements that we still don't know exactly how they're made in the stars, like as in which, more particularly what processes make them is less known. Yes. Isn't most of the universe? Yes, most of the universe is dark energy, followed by dark matter. And then ordinary matter is a very small percentage, like 5%. So everything we know is kind of like a very small percentage of the universe. So good question. That's the sort of thing we're kind of covering now. So basically, because the top questions, the top open unanswered questions right now are dark energy, what is it? Dark matter, what is it? And origin of elements. And pretty much really the top two questions would be about dark energy, dark matter. And as we just now said, pretty much that's the most, that's the most part of the universe right now. But actually, we've been talking about how the universe wasn't always like this. So in cosmology, we've been looking at, we just got into the topic of cosmology. So another thing I've been doing as well in the last couple of lives is kind of defining out what we mean by cosmology versus astrophysics versus astronomy versus particle physics. So again, if you wish to catch those discussions, you can go ahead and find those videos later on. But real quick, basically cosmology is the study of the universe, and it's much more cosmic scales, large scales. So for example, it's not just about this galaxy or the neighboring galaxies, it's really how the universe has evolved, for example, over time from its birth, from the Big Bang, to later on when the first stars started to evolve and develop, to like structure formation, like the various galaxies started to be. And even there is a study that people can do on the structure of the universe, because how the galaxies are in the universe is not a random distribution, but there is some structure to it. And people also try to figure out what this structure is governed by, what mysteries they might be holding. Things like that. So cosmic scale type of study of the universe is cosmology, and something like the Big Bang, something like the cosmic microwave background, something like understanding the universe's evolution in terms of its energy content, or the content of its energy density going from being more dominated by radiation to being dominated by matter to being now dominated by dark energy. And also dark matter. At this point, those are sort of a cosmology topic, okay? Astronomy and astrophysics have more to do with a study of specific astrophysical phenomena, so it's a much more specific thing. Astronomy is pretty much, if you're doing it with the naked eye, just looking at the night sky, if you're in a dark place, if you see all the stars and galaxies out there and planets, things like that, even that is sort of astronomy. Because traditionally, astronomy was just done with visible light with your naked eyes. And later on, we got telescopes, and it's much more to do with these heavenly bodies, so to speak. So objects in the sky that might interest you, sun, moon, other planets, their moons, our moon. By the way, our moon is one of the biggest moons in this solar system. fun fact, but we only have one. Most other planets, if not, I think all other planets in our solar system have more than one moon, whatever. Just being a little moon deficient over here. But basically, the more specific studies of the heavenly bodies or objects in the night sky, finding other Earth-like planets, finding other suns that might be the sun to other planets, studying sort of like a binary of two stars, for example, studying our own galactic center, figuring out that there is a supermassive black hole in there and affects things around it. Those are more of an astronomy and astrophysics type of topics. Okay? Now, of course, all of these have a lot of overlap, but I just wanted to give you some examples to kind of set your expectations. And then particle physics is, of course, later on in the later part of the 20th century and up to now, we have made a lot of progress in figuring out more particles and basically physics of the more small things, which really started in the 20th century at a fast pace with quantum mechanics developing a lot. So quantum mechanics came such a long way and gave us so many results and bizarre developments that we even have a whole field coming out now called particle physics, which of course gives us the families of particles. Some people classically did not really like this field because it seemed like every year they were discovering a new particle. But whether people like it or not, it's a thing. And there's lots of experiments and big budget type of efforts going on. And it's really dominated our more current and more recent efforts, including, of course, trying to discover newer particles. The Higgs boson was discovered in 2012. That was a big deal. I don't know how it has shifted our paradigm completely beyond what it was already shook up in the 20th century, because quantum mechanics itself shook things up a lot in the 20th century. So we talk about that earlier in our earlier lives, but basically in our earlier live streams, that is. But basically particle physics has evolved and given us families of particles. In short, there's leptons, quarks, and bosons, which are the fundamental particles. Now, dark matter, as you know, is an open question. We don't know what it is. So dark matter is sort of a topic that can be attacked or approached in terms of an astronomy or astrophysics point of view, as well as a particle physics point of view. And more recently that what we've been looking at is looking at it from a cosmological point of view. So keep an open mind. Yes, they still use the LHC. They do. So, so the reason for my little introduction here on the different types of fields is to kind of help with, oh, you're right. Yeah, Mercury is a planet. Has no moons. I forgot about Mercury. Thank you. Melly, do us a favor and tell us the moons of Venus then, the next one. So, thank you for contributing. Basically, the point about the different fields is also to understand that basically different topics can be kind of approached in different ways. And sometimes what can be answered by an astronomical, like an astronomy approach, might be kind of different than sort of a particle physics approach versus a cosmological approach. And sometimes when you're hearing about the different, say, candidates of dark matter, just keep in mind about the type of approach. So we saw from an astrophysics standpoint that they were considering for dark matter, for example, some of the candidates we spoke about from a textbook were neutrinos. This is a type of particle that's weakly interacting. It's low mass. And it turned out to be not such a great candidate for dark matter, but they did consider it. And especially because it was so weakly interacting and it did not interact with photons. So they thought it was a pretty good candidate, actually, for dark matter. And now this is sort of the type of candidate, which is, it's kind of like a both astrophysics and particle physics approach to trying to solve the dark matter problem. So keep in mind, sometimes you have to get these different fields to intersect and try from a few different approaches. So you might want to study, more of them in order to properly understand or in order to properly answer the question. So if you were considering neutrinos to be a candidate for dark matter, now I think at this point we are saying that neutrinos are not really a good candidate for accounting for most of the dark matter, for example, in our own galaxy. But they did consider it at one point. And it even probably influenced the next candidate that we talked about, which is WIMPs, weakly interacting massive particles, because they realized that the neutrinos are too low mass to really account for most of the dark matter. So why not basically imagine up a type of particle which is weakly interacting like the neutrino but has more mass, and maybe that can account for the dark matter-ness, And so there are searches happening even right now, experiments that are sort of in that intersection of astrophysics as well as particle physics and astronomy to answer the question of whether dark matter is something like the WIMP, weakly interacting massive particles. So you can imagine, those are the types of efforts. There are experiments and efforts trying to find something like a particle, and that would also give us the particle nature of dark matter. Now, in the current standard model of particle physics, we don't have a particle representing dark matter. So it would be sort of a new addition to the standard model. So some people might call this beyond standard model. So just keep in mind about the terminology, and that's what people mean. The other candidate we talked about from a textbook, and I'm mentioning about the textbook because sometimes we might consider, candidates that are sort of in a paper, and it's a lot more of a unconfirmed type of candidate or something that's not as serious of a candidate. But these candidates were considered pretty seriously or are still being considered seriously, and they are in the textbook that's being taught to students who, take this topic and pay money to go to school and stuff like that. So that's why I mentioned about that. So the next candidate we covered was the Macho, which was massive compact halo object. And it was basically like a dimmer, less bright, not really contributing to the luminosity in the galaxy type of a compact object, like a dim white dwarf or a brown dwarf or something like that, like a black hole that you can't see. And even that kind of fell short of being able to account for most of the dark matter in our galaxy, for example. But I keep saying our galaxy also to kind of make the distinction, because in astronomy, astrophysics, pretty much the scale of things would be probably our galaxy and other neighboring galaxies. So efforts that are kind of concentrated on our galaxy and other neighboring galaxies are sort of more in the realm of astronomy and astrophysics. If we're trying to do something with particles in the lab, that's more of a particle physics experiment. That experiment may not have any astronomers. I'm not saying that there shouldn't be any, but there can be sometimes these divides between the different types of fields in physics, and it's always good to consider them more holistically and broadly. What we're going to talk about now is yet another subfield. It's cosmology. It's the large-scale stuff that I was mentioning. And sometimes what cosmologists come up with and the types of things they consider might be very different and a very different approach. But the nice thing is that it looks like even in cosmology, there is actually very good evidence that we do need dark matter, and that there is this sort of difference in what we expected versus what we have matter-wise. And dark matter might also help us to understand things like what happened in the very early universe, going back to the very beginning, and also for something like structure formation. So its role is extremely important, it turns out, even on a scale of cosmology. So this is very important. So it's not just an our galaxy thing or the neighboring galaxies thing. It's a cosmologically important thing. So when something is motivated by so many by so many different aspects or angles, it truly becomes a very important topic. So keep that in mind going forward. Gluons. Why does the light emitted from stars not light up everywhere? Being bored is extremely good for imagination. You could imagine something while you're being bored and keep on listening at the same time. So thank you for being in the live. But basically, that's hopefully that kind of motivates for you the topic of dark matter. We didn't really talk about it too much yet, but I mentioned about dark energy as well. So now dark matter is basically this issue of not being able to account for all the matter in the universe, which is a pretty not bad, but which is a pretty concerning thing, because it leaves a lot of these big mysteries. But it also means that if we solve the problem of dark matter, it might give us a lot of insights about how the universe started and also how it developed. So when people look at, for example, like a picture of the distribution of galaxies, and they see that it's not really random, they want to know why. They want to know what is really governing this large scale structure. So there are people who only study this, like this is their niche. So something like this too would hopefully be eliminated, pun not intended, by dark matter, because dark matter is so very dark. So that's dark matter. Now, talking about let's see. Let me do one thing here. Thank you for all your questions, Smelly. Why does the light emitted from stars not light up everywhere? I'm not sure I understand. What do you mean not light up everywhere? So the stars are very far away. Actually, most of the stars in the sky are galaxies, and many of them are also binaries, and they're very far away. So it's hard to resolve them. And they, like the sun is a star, but is much closer. So it, is in that disk. And because it's much closer, the light goes everywhere. Is that what you're asking? About the other galaxies and stars, so the star closest to us is the sun. So in the daytime, the sun is pretty much dominating, and you can't even see any other things too much. But the other stars being far away is what... Okay, you're asking about gluons. Subatomic particle of a class that is thought to bind quarks together. So we'll get into it if you want. It's the mediator of the strong interaction between quarks. Honestly, there are so many types of particles. Gluons fall under bosons. So I mentioned that the three main types of particles are leptons, quarks, and bosons. Gluon is an example of a boson. So thank you for the question. Photon is also an example of a boson. Leptons are something like the electron and neutrino. So electron, of course, makes up ordinary matter, pretty common thing. So that's an example of a lepton. And then I mentioned quarks is the other third family of particles. Quark is what makes up protons and neutrons, for example. So I'm just giving you some examples. This is not the, what's the word? This is not the exhaustive list of everything there is to talk about in particle physics, but I wanted to just mention that those are pretty much... Hi, Baji! Oh, Baji is here. Those are pretty much... the particles, leptons, quarks, and bosons. And there's much more to talk about with regard to them, but I was mentioning it as as something that has developed in more recent times than the 20th century. Anyway, I think those were all your questions. Are gluons not a subatomic particle too, like leptons and quarks? Yes, they fall under bosons. The three types of subatomic particles are leptons, quarks, and bosons. Three. See? Three things. Okay. And they do use the LHC, Large Hadron Collider. All right. I think I answered your questions, Melly G. Hart. We will keep going. I wanted to introduce the topic as a whole. Now that we've done that, we will go back to cosmology. So pretty much, when people, so there's also a field called astroparticle physics. I worked in this myself. This is sort of in the cross-section of astronomy, astrophysics, and particle physics, where you're trying to, one way to put this is you're trying to learn more astronomy or astrophysics with a particle that is not the traditional visible light, basically. Because light also has a particle nature, right? So photons, you could say, well, all astronomy is done with this particle called light. But actually, you can have light that is like gamma rays, different wavelengths of light make up different ways of doing astronomy. So at this point, we do astronomy with much more than just the visible traditional light, but more so also with other types of light like X-rays, radio waves, microwaves, gamma rays, and depending on which part of the spectrum you're in that you're trying to collect data with, you're going to have a different type of detector. So actually, something like doing astronomy with gamma rays is also considered particle astrophysics because gamma ray, for example, is a very tiny wavelength light. It's much more of a particle-y kind of light than, for example, radio waves, which have bigger wavelength. So now, where it gets really interesting is sometimes you do astronomy with radio waves, but they're not necessarily coming directly from the source of the astrophysical phenomena, but actually you're picking up on the interaction of a different particle, and that particle is coming hopefully from the astrophysical phenomena. So, for example, particle astrophysics can also be done with a completely different particle than light, which could be something like the neutrino. So I worked on this myself. Neutrino, as I mentioned in a little bit ago, was an example of a lepton. It's a fundamental particle, very weakly interacting, has very low mass. It was even considered as a dark matter candidate at one point. But it's also a particle that is involved in or made with a lot of different, made in a lot of different nuclear reactions. The sun makes a ton of these as well. So does a lot of other astrophysical phenomena and other events in the sky. So sometimes we might even want to collect data on neutrinos that are potentially coming from different events or objects in the sky and learn about those events in that way. It's a different cosmic messenger than light, and it can give us a different kind of picture. But neutrinos are very difficult to measure depending on which type of neutrinos you're going after. And that itself can be a challenge. So we can talk about this more. But basically, this is another example of how astrophysics is done, how particle and astrophysics can mix together. What we'll talk about now, if you're ready, is the cosmic inventory. So we are referencing this book called Modern Cosmology by Scott Dodelson. He works at, I believe he works at Fermi. Yes, he works at Fermi National Accelerator Laboratory, University of Chicago. Lots of people in my field where I used to be also work at Chicago, U Chicago. Let me just catch my breath here for a second. Okay, but basically, as we delve into cosmology, you will notice that it's got a bit of a different approach than astronomy, astrophysics, and particle physics. Basically, in cosmology, we're very interested in understanding the universe, especially from learning about the early universe and whatever ways in which we can study the early universe, especially with something like the cosmic microwave backgrounds, which are photons from when the universe was 300,000 years old only. Given that the universe is almost 14 billion years old now, that was a very young baby universe from where we can have these photons. And we've measured these photons from that time. So we've learned a lot from it. And it's important to understand sort of the cosmic inventory. Like, what is the stuff that's in the cosmos? So in this particular part of the book, we will talk about that. So let's see what this is. And this should give you a pretty good overview. I'm just moving forward to see what there is. Armed with an expression for the energy density of a given species and a knowledge of how it evolves in time, we can now tackle quantitatively the question of how much energy is contributed by the different components of the universe. So there's this concept of energy density that we introduced in the last couple of lives. And with that in hand, we actually can quantitatively ask how much energy is contributed by each of the components of the universe. So what are the components of the universe? So I mentioned briefly that in the very early universe, when the universe was being born from the Big Bang, it was very radiation dominated. In other words, photons were the king of the jungle back then. So of course, photons is going to be a part of the cosmic inventory, and we will talk about them now. The temperature of the CMB photons has been measured extraordinarily precisely by the FIRAS, that's FIRAS, instrument aboard the COBE satellite. So we get around T equals 2.725 plus or minus 0.002 Kelvin for the temperature of the CMB, the energy density associated with this radiation. We have an equation for that and everything like that. There's a factor of 2, accounts for the 2 spin states of the photon. Great, because this is the photon we're talking about. The energy of a given state is simply equal to P since the photon is massless. See how that's the equation we're talking about here. The chemical potential is 0. We expect this theoretically because early in the universe, photon number is not conserved. For example, electrons and positrons can annihilate to produce photons. So the conditions were very extreme back then. And at those temperatures and how hot things were, photons were basically, all kinds of crazy things were happening at that time. And photons really dominated. And you couldn't really basically make stable neutral atoms and things like that. In that particular, I came into the ultra smart part of the stream. Yes. Hi, Doro, how are you? So we also know it observationally because the spectrum of the CMB has been measured so accurately. So because we know the spectrum of the CMB, we can measure it, that is, we can actually see the contents. The limits on a chemical potential are between basically mu over temperature less than 9 times 10 to the negative 5, so the mu can be safely ignored. Since there is no angular dependence in the integrand of that thing I just showed you, the angular integral yields a factor of 4 pi, and we're left with a one-dimensional integral. So some other integrals later, we basically have this expression for the energy. And to reiterate an important point, the photon energy density in this eventual equation depends on time via the scale factor. Scale factor is basically the small a factor we introduced earlier, which tells us about the expansion of the universe. And we also talked about how it actually depends on time, and how it depends on time has changed over cosmic history. But anyway, this thing depends on time via the scale factor, but has no spatial dependence. So this photon energy density depends on time via the scale factor, but has no spatial dependence. This is because we have used the zeroth order distribution function, the Bose-Einstein function for the photons. Bose-Einstein, of course, gives us a way to deal with bosons, named after Bose in the Bose-Einstein, and photons are bosons. In fact, there are small perturbations around this zeroth order distribution function. These do have a spatial dependence and correspond to the anisotropies in the CMB. So when we see the CMB, it looks very homogeneous. As in, it looks pretty much the same everywhere. it's it's like those photons were very much in equilibrium because we're measuring these really old photons. They did what they did, last scattering with electrons, blah blah blah. Then they're pretty much just coming to us. You know, they haven't done too much else. So they're in equilibrium and they don't have a lot of anisotropies, as in it's a very homogeneous picture to look at. But after looking and looking and looking for like 25 freaking years, they did find small, tiny, weeny, tiny, whiny anisotropies, and these might be very important. And the author is mentioning that we must, appreciate the spatial dependence through this type of thing because they might correspond to the anisotropies that does exist in the CMB, although they're not super obvious in the beginning. Okay, so pretty much here we have a way to do the math for the energy density of the photons. That's number one in our cosmic inventory. We know that photons really ruled the jungle back when it was early universe time. It was very hot, very, when the universe was just forming after the Big Bang. Photons were the main thing. And how the spatial or how the scale factor depended on time back then is different than what it ended up being once the universe became more matter dominated. So we can talk about that again, but we've mentioned it before that the scale factor's dependence on time has changed over time. And in fact, now it has changed again. And that's part of the reason why we think about dark energy, because we think that dark energy is actually making the scale factor's dependence change again, meaning the content of the universe is changing again. And it has changed a few times already. Okay, so the next thing in our list for the cosmic inventory is baryons. So I mentioned this before, that cosmologists kind of lump together protons and neutrons into a thing called baryons. They don't want to deal with protons and neutrons separately. They just call it all baryons. So let me read. Oh, yeah. Let's just see this little footnote here. So we'll talk about baryons. And then the author is saying, I refer to all the nuclei. I refer to all the nuclei and electrons in the universe as baryons. So not just neutrons and protons, it's also electrons. So pretty much all of the ordinary matter. In a previous chapter, he was mentioning that neutrons and protons are baryons, but now he's saying he's basically considering electrons to be part of that too. He doesn't want to, differentiate between these things. This is technically incorrect. That's right. Yes, good. In this part of the chapter, he's saying that electrons are part of baryons, but I just wanted to mention that generally speaking, baryons are neutrons and protons, and electrons are a different type of particle. They're leptons technically, but for this discussion, he just wants to lump them all together. But nuclei, so he's saying technically electrons are leptons, but nuclei are so much more massive than electrons that virtually all the mass is in the baryons. So because he's trying to do a cosmic inventory, it doesn't really matter. And he's saying baryons will include protons, neutrons, and electrons for this particular discussion. Okay, so unlike the CMB is of course the cosmic microwave background, which is the photons, and we just talked about photons. That was number one on our list. Next, what's in the cosmic inventory is the baryons. Baryons cannot be simply described as a gas with a temperature and zero chemical potential. So when we were trying to write down the equation for the photons, it was nice because we have tools in our bag given to us, for example, by Bose-Einstein, which give us a way to deal with photons. Photons are bosons. We have things we know about them, equations that we can write down about them. But baryons are a little bit more different and complicated. So the baryon density must be measured directly, not via a temperature. So the nice thing with the photons was, we had a temperature for the CMB, so that gave us a part of the equation, and then we have ways to write down the equation from Bose-Einstein, but how are we going to write the equation for the baryons is going to be a little different, is what he's saying. So there are now 4 established ways of measuring the baryon density, and these all seem to agree reasonably well. These are all measurements at different redshifts, and we know that the density scales as a to the minus 3. So to facilitate comparison, one defines this big omega baryon via rho b over rho cr, and that will equal to the big omega b times a to the minus 3, where the small a is the scale factor. So the scale factor, scale factors dependence on time has changed. So this is how it all kind of binds together. We know that the scale factor's dependence on time has changed. The universe is behaving differently in different epochs, basically, because in some parts of its evolution it was more photon dominated, and in other parts it's more matter dominated, according to all of this. So this omega b is the ratio of the baryon density to the critical density today. The simplest way is to observe the baryons today in galaxies. The greatest contribution to the density, though, comes not from stars in galaxies, but rather from gas in groups of galaxies. So something that people forget about is that galaxies have a ton of gas, and you'd be surprised that actually, in addition to the stars, all of this gas actually contributes a lot to the ordinary matter that we know of. So in these groups, omega b, which is the baryon thing, is about 0.02. The second way to count baryons is by looking at the spectra of distant quasars. The amount of light absorbed from these beacons of light is a measure of the intervening hydrogen, and hence the baryon density. So smart ways, right, of figuring out the baryon densities. Cool. These estimates suggest this number of around 0.02 with a fairly large uncertainty. A third method is to infer the baryon density by careful scrutiny of the anisotropies in the universe. So once again, those anisotropies are important. Ooh, their food is falling. Hi, Groove Toot, how are you? Their foodie is getting ejected. Stay with us for a while. So once again, the anisotropies are important because basically the thought is, even in the early universe, even though that was mostly photons, whatever anisotropies would have to be, would have to be explained by other things, whatever the other things might be. It could be ordinary matter, it could be dark matter, who knows, that sort of thing. So finally, we will see in chapter 3 that the light element abundances are sensitive to the baryon density, and that estimates of these abundances pin down this number we have to 0.025 plus or minus 0.0018. So because we also have light element abundances, what are light elements? It's mainly hydrogen, helium, little bits of lithium, depending on who you talk to. Pretty much astronomers think of all the elements over helium as metals, but light element could, I guess, be some of the initial elements in the periodic table: hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, blah blah blah, oxygen, those types of things. But pretty much, though, in the universe, the most abundant element is, of course, hydrogen. It's the first thing that was able to form. And other things matter a lot less. Okay, so you don't have to know the whole periodic table when you're considering astronomy or cosmology, thank goodness. Chemistry, of course, they care about the periodic table immensely, but in astronomy, pretty much hydrogen is the main thing. And everything else is still important, but much less important. Remarkably, then, these, and cosmology also as well, because cosmology is the study of the universe, and the universe mostly has hydrogen. Even our sun is making helium from hydrogen. It's what it does. It's got one job. Hopefully, it does it really well, because that's where we get all our power, energy, and light from. Remarkably, then, these estimates of the baryon density with very different techniques all agree. So the nice thing is that they had different ways of calculating the baryon density, and they agreed, thank God. They all placed the baryon density at roughly 2 to 5% of the critical density. So this is the critical density of the universe. And the baryon density is contributing to 2 to 5% of this critical density. The total matter density in the universe is higher than this. So there must be matter in the universe that is non-baryonic. So this is the big clincher for dark matter being non-baryonic. Not only do we know that dark matter, of course, you can't see it. We know from astronomy measurements and from the rotation curves of stuff in our own galaxy even, that there's this extra matter that's not luminous, and that created a lot of issues for us to explain what exactly this what exactly this extra matter is made of. But now, from the cosmological point of view, we basically get further confirmation that this thing, this dark matter that we call dark matter because we can't see it, quite literally, we can't see it, it's invisible, but it's affecting gravity, it's making things go faster. We covered this a little bit from an astrophysics point of view. We saw the orbital speeds of things that are far away from the galactic center in our own galaxy. Basically, the orbital speeds are too high, given our understanding of where most of the luminosity of the galaxy is coming from and what mass accounts for that. And then we see that there's this extra mass that you have to have. And so it's highly... Yes, books and cats and physics. So it's highly confusing. It confused people from an astrophysical point of view. To find all this extra mass, or the evidence of extra mass, even in our own galaxy, is a highly concerning thing. Then they pretty much see that it's a thing for our neighboring galaxies too. But even to find it in our own galaxy is a big deal from an astronomy and astrophysics point of view. It means that we don't understand our own galaxy. That's pretty bad. Or if not bad, it's concerning. It's a big open question. But now, from this cosmological discussion, we're finding that there is a cosmological point of view to all of this as well. And from the cosmological equations too, we are finding that baryonic density is contributing to only 2 to 5% of the critical density of the universe, and the total matter density is much higher than that, which means that dark matter is non-baryonic. It's not made of neutrons, protons, and electrons. Unfortunately for us, because we can't see it, and nor have we found a way to see it yet. So makes it all the more intriguing. Thank you, Doro Doro. This has to be the most unique combo. A dang good one. Education and cats. Thank you. Yes, we do books and cats, booktuber, catfluencer type of thing. And we cover mostly physics from my own background. Or my background is in physics, so I cover topics related to that. So anyway, the next thing, okay? We talked about photons, we talked about baryons. Now we will talk about matter, just matter, and we'll see what he means by that. All of the methods of measuring the baryon density mentioned above involve the interaction of matter and radiation. For example, simply counting stars works at some level because we roughly know how much mass is required to output the light from a typical star. So the nice thing is that astronomy is so old, we have all these clever ways of knowing what the mass of a thing is, depending on the luminosity of it, blah, de blah, de blah. And so we kind of can tell pretty good, about the mass of a star, for example. And it turns out that the mass of a star is actually extremely important. it affects a lot of things. We saw even how the mass of a star is actually what's going to tell you how it will die and what kind of stellar remnant you would get. We covered that at one of the live streams. We said, depending on the mass of the star, you would either get a white dwarf or a neutron star or a black hole as the stellar remnant. So, nice thing is, some things are more simple than others. This is one of those nice things where we know what the mass is depending on. Hi, Arbin. Hello, sweetie. How are you feeling today? I'm all right. How are you, Arbin? Anyway, for example, simply counting stars works at some level because we roughly know how much mass is required to output the light from a typical star. There are, however, methods of measuring the mass of matter that do not rely on the way light and matter interact. So, what I just said, the thing about the luminosity and the mass, of course, is an issue if your mass is not contributing to luminosity, right? So, like a light thing, basically what we saw with dark matter is that it does not contribute to the luminosity in the galaxy, which makes it such an issue for us to figure out, like, that it's even there. And if it's there, what is it, right? So we have to figure out some other thing. Now, well, thankfully, of course, it does interact with gravity, right? Thank God. So these classically, the methods for understanding matter that has nothing to do with light classically have involved measuring the gravitational field in a given system, thereby inferring information about the mass responsible for that field. So here's a little figure for you. This shows the inferred mass to light ratios of many systems ranging from galaxies to superclusters. Historically, this ratio was measured on small scales first, suggesting that the density in the universe was far less than critical. As more large-scale data were obtained, the steady increase in the mass to light ratio led some cosmologists to speculate that eventually we would find that the density was critical. Bacall and collaborators, however, have argued that mass to light ratios do not increase past when the radius is around megaparsec. A leveling off occurs consistent with a matter density of around 0.3, where this omega matter now is the ratio of the total matter density today to the critical density. Recently, a number of other techniques for inferring the matter density have emerged. We will see in Chapter 7 that the distribution of galaxies in the universe in particular, so I was talking about this earlier, the distribution of the galaxies in the universe is also important. It's not random. There is a rhyme to that madness, and we will see, The distribution of galaxies in the universe, in particular, the power spectrum of this distribution is very sensitive to omega m times h, where omega m is the matter density. And what is h? I forget what h is. What is small h? Why say what small h is? We probably said it in a different context. Whatever. Is very sensitive to the matter density times small h. Virtually all galaxy surveys have inferred that this thing is 0.2, the small h times matter density. Another cosmological hi Mac tonight. Thank you so much for your intriguing way of doing things. Okay, so basically, thank God, there is more ways than one to know the matter density. We talked about the baryonic density, and it was mainly to do with light, light ways of doing things, like things where you observe light from quasars and what's getting absorbed and all that stuff. But now we're talking strictly about matter density. This is more than just the baryonic matter. Okay, what's the last message here? Hello, sweetie, how are you? Okay, yeah. Okay, so now that we're getting a number of 0.2, 0.2 for that. Remember that the baryonic omega was 0.0205, and now we're saying that the matter omega, so the matter density, is 0.2. That's quite a bit larger. Another cosmological probe we will encounter in chapter 9 is the cosmic velocity field and its relation to the observed galaxy distribution. These are related by the continuity equation, a relation sensitive to the matter density. Again, most of the measurements are clustered around the matter density of around 0.3. So they're doing other ways of finding this matter density now, like other types of probes. Another way of measuring the total mass density is to pick out observations sensitive to the ratio of the baryonic density to the matter density and use the apparent value of the baryonic density to infer the matter density. For example, most of the baryonic mass in a galaxy cluster is in the form of hot gas. So we mentioned how actually in a galaxy cluster, most of the baryonic matter is in the hot gas, not in the stars, as you might think. The ratio of the mass of gas in clusters of galaxies to the total mass can be measured either by looking for X-ray emission or by looking at the electron-heated CMB in the direction of the cluster. If this ratio is characteristic of the universe as a whole, and it probably is because clusters are so large, then the cosmic baryon to matter ratio is around 20%. So all of this is to come to this particular ratio here. Since baryons make up only 5% of the critical density, the total matter density is inferred to be about 0.25. Another way of inferring the baryon to matter ratio is by looking for features in the power spectrum of galaxies. If the baryon fraction is truly of order 20%, then there will be wiggles in the spectrum. There are tentative hints of these wiggles in the early data from the 2-degree field survey, a survey we did in 2001. These pin down omega baryon to omega matter to around 0.15, consistent with the cluster observations. So things are kind of agreeing. Finally, the anisotropies in the CMB are sensitive to the matter density. Recent determinations indicate that the matter density is around 0.16. Again from 2001, another study. Given the fact that current best estimates of the Hubble constant, small h is the Hubble constant. Sorry, forgot about that. Hubble constant is around 0.72. The CMB observations also are consistent with a matter density equal to 30% of the critical density. So all these different ways of getting the matter density as well as the baryonic density tell us the following, which is that we therefore have an enormous amount of evidence telling us that the baryon density is of order 5% of the critical density, while the total matter density is some 5 times larger. Most of the universe, most of the matter in the universe, not the universe, most of the matter in the universe must not be baryons. It must be some new form of matter, which is dark matter. So yeah, most of the matter in the universe must not be baryons. So they did a number of measurements to figure out, and different types of measurements too. So I mentioned some of the ones have to do with light and interaction of matter and light. Some of the ones don't have to do with light. They're just gravitational field type of measurements. All of these and all these different surveys basically gave us that the overall matter density is around 30% of the critical density, and the critical density is that of the universe. So it's basically the overall content of the universe, and we're getting that baryonic matter is only 5% of that. So baryonic matter is neutrons, protons, and electrons. Ordinary matter, in other words, is only 5% of the matter density. So that leaves us with like 25% of the universe is dark matter. and we don't know what that is. So, this is the cosmological evidence of dark matter. We have covered astrophysical or astronomy evidence of dark matter in a previous live stream. In a couple of different live streams before, we covered how we understood that there is dark matter in our own galaxy. It was an astronomy kind of finding, astrophysics kind of finding. Now we're talking about a cosmological standpoint and how by studying the universe and what we expect the content of the universe to be, and we have this thing called the critical density of the universe's content, and understanding how baryons contribute to that, we have found that 30% is all matter density and only 5% of that is baryonic. So the rest is non-baryonic, and we call that dark matter because we do not know what that is. So, thank you for being here. We will now go to the next cosmic inventory. So far, so good. We have covered photons, cosmic inventory number 1, photons, number 2, baryons, number 3, just matter in general. Baryons are a part of that. Next, we will talk about neutrinos, my favorite particle. This too is a component of the universe. So the next component we need to consider is the neutrino. Thank you for being here, Arbin Ali. Thank you for asking. You're a great describer. Thank you. So the next component we need to consider is the neutrino. Unlike photons and baryons, so I mentioned how baryons are protons, neutrons, and electrons. Actually, baryons more correctly are just the protons and neutrons. The author lumped in electrons with the baryons in this particular current discussion because it's just easier to do it. Neutrinos are a type of lepton I mentioned earlier in the particle family. So different fields have different ways of describing things. Basically, in the particle physics field, electrons and neutrinos are in the same family. They're both leptons. In terms of the cosmology discussion that we're having right now, we lumped electrons together with protons and neutrons and just called them all baryons. You might think that neutrinos are a part of that, but not really. Neutrino is another thing. In the cosmic inventory, they get their own category. Okay, so we will talk about that right now. The next component we need to consider is the neutrino. Unlike photons and baryons, cosmic neutrinos have not been observed. So arguments about their contribution to the energy density are necessarily theoretical. Wait a minute. Astrophysical neutrinos have been observed. So don't bother her, Baji. So I don't know what the... Oh, you know what it is? Cosmic neutrino... Wait a minute. Are they talking about the neutrinos that come from... So I'm not so sure that cosmic neutrinos have not been observed. Maybe at the time of this writing, they were not. But anywho, we'll keep going. Basically, at this time, we have observed a number of astrophysical neutrinos, for example, by the Ice Cube Observatory. So if you're hearing something about high energy neutrinos from this discussion, take it with a grain of salt and just look it up later on whether, because, you know, neutrinos are a hot topic and developing topic. I want to double check whether at this time we have observed the neutrinos that he's talking about or not. But pretty much there might have been some updates to that. But we'll keep going with the discussion. He's saying theoretical arguments are quite strong based on very well understood physics. Basically, yes, there are both cosmic and astrophysical ways in which neutrinos can be made. And we have experiments set up to measure them. I'm kind of blanking on what this person might mean by cosmic neutrinos, but I think I know what he means. And It's fine. There has been more developments in the science of neutrinos since this book was probably written, so I'm not surprised. A basic understanding of the interaction rates of neutrinos enables us to argue that neutrinos were once kept in equilibrium with the rest of the cosmic plasma. So neutrinos are a very different type of particle than what we've discussed so far in the context of cosmology, in the sense that in general, neutrinos are very weakly interacting. I mentioned them a little bit when we considered them as dark matter candidate in one part of our discussion. They're weakly interacting leptons and very low mass particles, and they do not interact with photons. So detecting them is actually quite difficult as well, depending on their energy and source and things like that, and how much of the type of neutrino there is from that particular event. So basically, though, they are made all the time, so they're not uncommon, but depending on, the particular source you might be wanting them from, et cetera, it can be kind of difficult. A basic understanding of the interaction rates of neutrinos enables us to argue that neutrinos were once kept in equilibrium with the rest of the cosmic plasma, since they're fermions, so they're leptons, same family as electrons. Their distribution was Fermi-Dirac with zero chemical potential. At late times, they lost contact with the plasma because their interactions are weak, so they don't interact with the same way as electromagnetic type of interactions. They have the weak force is what their interaction is. Nonetheless, their distribution remained Fermi-Dirac with their distribution remained Fermi-Dirac with their temperature simply falling as a to the -1. The main task, therefore, is to relate the neutrino temperature to the photon temperature today. The tricky part of this is the annihilation of electrons and positrons when the cosmic temperature was of order the electron mass. Neutrinos lost contact with the cosmic plasma slightly before this annihilation, so they did not inherit any of the associated energy. The photons, which did, are therefore hotter than the neutrinos. We can account for the annihilation of electrons and positrons by using the fact that the total entropy density S scales as a to the -3. Massless bosons contributes this thing 2 pi squared T cubed over 45, where T is the temperature, to the entropy density for each spin state, while massless fermions contribute 7/8 of this, and massive particles contribute negligibly. Before annihilation, the fermions are electrons, so they have 2 spin states. Positrons also 2 spin states, because positrons are just electrons of the opposite charge. Neutrinos, 3 generations and 1 spin state, and antineutrinos, which is the 3 again. So the bosons are photons, 2 spin states. So now we will do some spin state bookkeeping to figure out that this equation for the neutrino is what it is. It's like over here. So after some bookkeeping and whatnot, we get this T nu neutrino over T gamma. We get 4/11 to the 1/3. So we basically have a way to evaluate the energy density of neutrinos in the universe. Let's sum up what we know about the cosmic abundance of neutrinos. Basically, because we know that neutrinos lost contact with the cosmic plasma slightly before this annihilation, we kind of know the interaction that happened that did that. So we will do a bunch of bookkeeping, knowing what types of particles were in the mix of things, and give the neutrino its proper account. So we can now evaluate the energy density of neutrinos in the universe. Let's sum up what we know about the cosmic abundance of neutrinos. 1 spin degree of freedom for neutrinos. Neutrino has an antiparticle. 3 generations of neutrinos. We know that there are 3 types of neutrinos, electron, muon, tau. Under the lepton family, neutrinos are fermions, so they will get the Fermi-Dirac distribution function. Neutrino temperature is lower by a factor of 4/11 to the 1/3, since photons are heated by the electron-positron annihilation. So photons were heated by this, but not neutrinos. So photons are hotter. The first three items on the list then imply that the degeneracy factor of neutrinos is equal to 6. Right, because there's 3 generations of neutrinos. Neutrino has an antiparticle, and there's 1 degree, 1 spin degree of freedom. So the first 3 items on the list then imply that the degeneracy is equal to 6. The fourth means we need to change the denominator in the, yes. We will make it Fermi-Dirac, and then finally, since the energy density of a massless particle scales as t to the 4, it's fine. He's saying that the neutrino is massless. It's not really, but okay, whatever. It's an estimate. So basically, he puts it together to get a rho or a density for the neutrino. I guess he made them massless. They do have a mass. Equivalently, if there were 3 species of massless neutrinos today, then their contribution to the energy density would be what? Oh, okay. All right. It's small. In reality, all the neutrinos do not appear to be massless. So this book is a little old. Neutrinos do have mass. They're just low mass. Observations of neutrinos from both the sun by Bakal in 1989 and from our atmosphere 1998 strongly suggest that neutrinos of different flavors oscillate into each other. They do, electron muon and tau neutrinos. This can happen only if the neutrinos have mass, thank God. The atmospheric neutrino observations in particular imply that at least one neutrino has a mass larger than 0.05 eV. So this will kind of change the equation a little bit. At high temperatures, this reduces. So when we consider that neutrinos in the early universe, it's sufficient to use some... Oh, I see. Oh. Without 3. Okay, so it becomes more simple in the end. Those who trafficked in both astrophysics and particle physics early on noted that the simple observation that the total density was not much greater than the critical density leads to constraints on neutrino mass, constraints much more stringent than those obtainable at accelerators. Wow. When the need for non-baryonic dark matter first became evident, a number of cosmologists proposed neutrinos as the natural candidate. See? Wow. So not just the astrophysics people, or maybe it was the cosmologists. Basically, the neutrino was a very natural first candidate for dark matter. They thought that maybe there is, we just didn't account for the neutrinos properly because we did the baryonic density, the matter density, and neutrino is kind of different, right? So maybe neutrinos will make up the difference. Subsequent studies of the structure of the universe with neutrinos as the dominant dark matter component looked significantly different from the actual universe. But unfortunately, even for our own galaxy, neutrinos don't really account for most of the dark matter that's in our own galaxy. And also, turns out, as far as cosmological standpoint goes, it cannot explain the structure of our universe. Nonetheless, the possibility that neutrinos might make up a fraction of the total density re-emerged in the 1990s. We can then hope to detect a trace amount corresponding to masses smaller than an eV by observing its effect on large-scale structure. Wow. So yeah, neutrinos will contribute some fraction to the total energy density of the universe. And people probably even got excited because the neutrino was getting discovered and they were probably thinking, oh my gosh, the neutrino is very weakly interacting. You can't, see it very easily, quite literally see it, right? Like with photons, they don't interact. So people probably got really excited to think that it might account for dark matter, but it doesn't completely. It might account a little bit of the fraction, but mostly doesn't. It's too low mass to account for dark matter, and also it does not give us the, as this person is saying, the cosmological argument is that it does not contribute. Like if you put in the neutrino as the dark matter model, then you don't get the structure of the universe developing as it did. So structure of the universe, structure formation in the universe, and how it evolved, as in distribution of galaxies, even within the galaxy, how things happen, is very much governed by, we think, by dark matter. So then, say if you have a model and you put in the neutrino in that, it doesn't really lead to the structure of the universe that we see, the actual universe. So that's why this is one more way in which the neutrino was discarded as a serious candidate. But it was a serious candidate. It was considered. So even in that astrophysics book we read, we saw the neutrino was the first candidate for dark matter. And it is good to understand why, right? It's good to understand because it can actually help us in other ways. Some of the dark matter experiments are a little bit like neutrino experiments, you know? So it's almost like if you did a neutrino experiment or a detector, you might be well equipped to, make a dark matter detector, because some of it might have overlap in what you expect dark matter to be like. So neutrino was considered. Unfortunately, it doesn't really account for the mass we would need. And cosmological standpoint, cosmology has a bunch of models. They very much have to like bookkeep everything based on these things. And they found, again, with cosmological standpoint too, that the neutrino didn't really explain structure formation in the universe. So we let it go as a dark matter candidate, at least for now, until we find more information on it. So yeah, that was neutrino. So we have now covered, under cosmic inventory, we have covered photons. These were very important in the early universe, pretty much dominated the early universe. Then we covered baryons. In this discussion, we considered them to be both protons, neutrons, as well as electrons. Basically, all of the, most of the ordinary matter. Then we also considered the calculation that goes into matter density, what we consider to be basically contributing to the overall matter density of the universe. And from a gravitational standpoint, what do we get? And upon comparing that to the baryonic density, we found that baryonic density was only accounting for 5% of it. So out of like 30%, 5% was baryonic. The rest was dark matter, which we know not what that is exactly. Then in the cosmic inventory, we considered neutrinos, and we learned a lot about that. We have some equations for that. Neutrinos are fermions, so that helped because we can write them down as Fermi-Dirac equations. They're very low mass though, so they did not help much to account for dark matter. And the next candidate, if you're ready, the next candidate or thing in our cosmic inventory is gonna be, somebody guess. It's gonna be dark energy. Yay! I have to use the bathroom and charge my phone. I'll be right back. Hi, Disco David. Is my phone charging? Okay. Here we go. You can look at it for the time being. We are on dark energy next. Okay, so basically, we are going over cosmic inventory. Hi, Doro Doro. We are going over cosmic inventory. We have covered photons, baryons, overall matter density, neutrino density, and now we're going to do the last thing in the cosmic inventory, which is dark energy. And we saw how the overall matter density was much bigger than the baryonic matter density, giving us yet more evidence of dark matter, type of matter that is not baryonic and not ordinary. We also saw that neutrinos, which is a type of leptons, as well as a type of fermion, basically depending on how you describe things. In particle physics, they would be considered basically under the lepton family. They also happen to be fermions based on their spin and such. We learned a little bit more about neutrinos. And we even saw that people got excited about them because people thought that this might account for dark matter, neutrinos, but they do not, unfortunately, but not a bad guess. Next in the cosmic inventory, and last but not least, might even be the most interesting, is going to be dark energy. We will continue this in just a second. I have to use the bathroom. I'll be right back. Enjoy, guys. What the heck? Says Doro Doro. I teach college. Okay, Disco David, have a good night. Love the name. How very interesting indeed. Thank you for liking the live, by the way, guys. Thank you so much. Thank you for liking, subscribing. All that stuff really helps the channel. Thank you. BRG. Be right back. I teach at Harvard. Okay. Thanks for asking. We are covering cosmic inventory. All right. You should cover the Civil War next. I'm a big fan of the Confederacy. Confederacy. We will cover dark energy lastly as part of the cosmic inventory. We will cover dark energy lastly as part of the cosmic inventory. There. Disco David, why don't you take a spin around the block? Show us your disco while you're in timeout for 30 minutes, okay? Thank you so much. Be right back, guys. I'll be right back. Off and off. Vertically up and off and off and off and off and off and off. Good. really funny. Baji. Oh, mommy, Shuji, mama. Oh, I'm so sorry, Shuji, mama. Mama's back. I'm so sorry. All right. She fell asleep. Thank you, Dora. You're so sweet. Thank you so very much. Thank you, everybody, for being here. Y'all are funny. Okay. So we will now talk about dark energy. I want to get some water. So, one more second, please. Oh, Suji. Suji went and got me. She said that you guys were being very confused about what mom is doing. And so she went and got me from upstairs. I did have to use the bathroom. Where are you, my balls? Suji. Hey, Baba, Suji. Here you go, babies. God, it's cold down here. Okay. All right. And not only that, Suji told me everything that we missed that was happening. And I will now make myself some wawa. Excusez-moi. Sorry about the coughs. Actually, let me just boil. Let me make some tea water. I'm gonna boil some water. Give me one more second, guys. I want to boil some tea water. It's too cold not to make some tea. It snowed in Boston this morning, early in the morning. Doro and everybody, thank you so much for being here. Hello. We're back. We're talking about cosmic inventory. Yay. Thank ya. Hi, Shona Pucci. Embrace the what? Okay. Too cold. Embrace the patriarchy. What's the meaning of that? Annie Frank. Hello. Well. Thank you once again, everybody, I am choking on something akin to, I think, just saliva. All right. We will get to dark energy here very soon. So, about this cosmic inventory, basically, we have covered photons, baryons, matter density, as well as neutrinos now. And we will do dark energy next, like that. Mick, hello. Hi, Grimace. Good value deals at your local McDonald's. So, we'll get started actually as the tea stuff is happening. There are two sets of evidence pointing towards the existence of something else. So we've done photons, we've done baryons, we've done matter, which showed us another way of getting the total matter density. So not just the interaction of matter and light, but also to see gravitationally what was the density of matter that we were getting as part of the energy density of the, or the critical density of the universe, which would be the content of the universe. And we saw that ordinary matter or baryonic matter, including electrons in this case, was only about 5% of the total matter density, which was around 30% of the critical density, meaning 25% or so is dark matter, which is really concerning and a big open question of the universe right now. Then we also looked at neutrinos and neutrino density. Since neutrinos are leptons and spin-wise they're fermions, meaning we can write down the Fermi-Dirac equation for them. We can also deduce certain things from the fact that it would have interacted with some of the early photons, and since we know the photon's temperature, we can do some things with that as well. And then, as part of the cosmic inventory, we come to dark energy. This is something that we have mentioned on the channel before, especially a while ago when we covered Einstein's Cosmos by Michio Kaku. We talked about how over 100 years ago when Einstein was writing down his equations and he saw that you had to stabilize the universe against gravity, you needed something called the cosmological constant. He called it a placeholder to kind of just make the universe stable and not collapse on itself. This was called something like cosmological constant, and something like it was hypothesized as maybe like this energy of the vacuum or dark energy. It is still something that we talk about now, and it's still a bit of a mystery, and it is an important, you will see, very important part of this cosmic inventory. So that's what we talk about next here today, and thank you again for being here. You should teach physics at your... Oh, okay, thank you. All right, so let me get a few sips of that tea before I speak a lot more. Sorry about the coughs. Birdie. Head to McDonald's. Get a good price. Really? Okay. Is McDonald's sponsoring this live? If so, not a bad idea. You're smart. You've got money. Not sponsoring. Wow. For the money emoji. Sponsor is always appreciated. Yay. Alright. Almost done with the tea. It boils very fast. Hi, Fuji. So, there are two sets of evidence pointing toward the existence of something else. Something beyond the radiation and matter itemized above. The first comes from a simple budgetary shortfall. The total energy density of the universe is very close to critical. We expect this theoretically, and we observe it in the anisotropy pattern of the CMB. Yet, the total matter density inferred from observations is only a third critical. The remaining 2/3 of the energy, or of the density in the universe, must be in some smooth, unclustered form, dubbed dark energy. The second set of evidence is more direct. Given the energy composition of the universe, one can compute a theoretical distance versus redshift diagram. This relation can then be tested observationally. So this is where we get the observational evidence. In 1998, two groups observing supernovae reported direct evidence for dark energy. The evidence is based on the difference between the luminosity distance in a universe dominated by dark matter and one dominated by dark energy. So we will look at figure 2.3. Where are you? Hello. This is figure 2.3. This sort of stuff, okay? Now let's look at what he says. This indicates the luminosity distance is larger for objects at high redshifts in a dark energy dominated universe. So the that makes sense. Luminosity distance is larger for objects at high redshifts in a dark energy dominated universe. Therefore, objects of fixed intrinsic brightness will appear fainter if the universe is composed of dark energy. Ooh, also, there's a footnote. After the discovery, quite a bit of attention was focused on choosing an appropriate name. So this dark energy business, the name of it, right? Cosmological constant is something we mentioned before on the channel. Cosmological constant was really the initial name. It was too restrictive to that, in that the energy density is constant at all times, and we do not yet know that this is true of the dark energy. Variable cosmological constant fixes that problem, but introduces an inherent contradiction. Variable and constant, variable lambda using the Greek letter reserved for the cosmological constant is too obscure. Quintessence is a good choice. It expresses the fact that after cosmological photons, baryons, neutrinos, and dark matter, there is a fifth essence in the universe. So we talked about photons, baryons, neutrinos, and dark matter. There is a fifth essence in the universe. It seems to me that dark energy has become a bit more popular, with quintessence referring to the subset of models in which the energy density can be associated with a time-dependent scalar field. I play this while I'm drinking and driving. Oh, good. Your comments are wild. But I gotta be at the office tomorrow. It's bedtime. Have a good night. Duru Duru, have a good night. Thank you. Thank you for being here. You can catch the whole live stream as a video upload later on, maybe when you're working. And yeah, if you want to play it in the background. So that's a little bit of a note right here that we just read about the nomenclature here for dark energy. You know, basically it all started with the cosmological constant. Einstein had to write that down as part of his equations to describe the universe because he basically realized you need something there to go against gravity and to stabilize the universe. Little did he know when he was reluctantly introducing this cosmological constant being what we called it back then, and even now sometimes, it became something very important. It wasn't just about the equation, it became such that not only was the universe stabilized by this, turns out the universe was actually expanding, then turns out that the expansion of the universe was actually accelerating. So whatever this concept was, which the cosmological constant introduced, which we dubbed as dark energy, turned out to be very, very important. And as we find out now, from all the cosmological cosmology math of the critical density of the universe, it turns out to be a very large portion of the content of the universe, which we'll get into right now. Perfect. So we will keep on going. Give me 1 second, actually. I want to make this tea before we keep on going because I need it. Thank you, everybody. Could you please like the live too while you're at it? Keep going down the path of... Okay. All right. If you insist. Wrinkle. Off and off. And off. Off and off and off. Okay. Have the water and now in the mug. So, as I was saying, this cosmological constant was the initial name given to this whole concept. But then later on, it turns out that really what we're after is, in terms of cosmic inventory, the energy density of whatever this thing is, which we dub as dark energy, well, it would be changing, right? It's not the same throughout the evolution of the universe. So even though we called it cosmological constant, when we introduced it, when Einstein introduced it, if we keep calling it cosmological constant, even though that's where it stems from, it's kind of confusing because we don't expect the energy density of dark energy to be a constant throughout the evolution of the universe. So we need to come up with a different name, but it was already being called sort of this dark energy name. So that's what we've stuck with. So that's what we're talking about now. It's the fifth element of our cosmic inventory. Fuji's on it now. Boston. Mm-hmm. Mm-hmm. It's the fifth element of the cosmic inventory after photons, baryons, neutrinos, and dark matter, because we found that there is also something called dark matter that we have to consider, given that most of the matter density was not accounted for by the baryonic density. So we needed dark matter. So after photons, baryons, dark matter, and neutrinos, the fifth thing that we must consider is this thing called dark energy, which we will now talk about, or keep talking about. So first, First comes the simple budgetary shortfall. The total energy density of the universe is very close to critical. We expect this theoretically, and we observe it in the anisotropy pattern of the CMB. Yet the total matter density inferred from observations is only a third critical. So basically, what that is saying is that if matter density is about a third of the total energy density, then the rest has to be something else. And we know that in the early days, hi Fuji Baba, it used to be radiation dominated, and the scale factor was dependent on time as t to the 1/2, I believe. Later on, it changed to t to the 2/3. So as the content of the universe kind of changes, so does this type of dependence. And we can kind of observe these things and determine also from that how these things have changed. So the remaining 2/3 of the density in the universe must be in some smooth, unclustered form, dubbed dark energy. The second set of evidence is more direct. Given the energy composition of the universe, one can compute a theoretical distance versus redshift diagram. So that's what we're talking about next as the more direct evidence of dark energy. This is quite interesting, actually. This relation can then be tested observationally. In 1998, two groups observing supernovae reported direct evidence for dark energy. The evidence is based on the difference between the luminosity distance in a universe dominated by dark matter and one dominated by dark energy. So dark energy makes the universe expand, right? So you would get those, the luminosity distance is larger. So you would get those intrinsic brightnesses to appear fainter because they're basically getting pushed out. So the luminosity distance is larger for objects at high redshifts in a dark energy dominated universe. So luminosity distance is larger for objects at high redshifts in a dark energy dominated universe. Therefore, so high redshift means like far away, you should be seeing that the galaxies are getting like pushed out, like our distances are getting larger between us. Therefore, objects of fixed intrinsic, because this is a cosmological effect, the expansion of the universe, so you might not notice it between like us and the neighboring galaxy, but at high redshifts, you should be noticing this. Therefore, objects of fixed intrinsic brightness will appear fainter if the universe is composed of dark energy. So that's the more direct evidence. More concretely, distance of equation 2.50. What is equation 2.50? It's fine. We will summarize it. The two groups measured the apparent magnitudes of dozens of type 1a supernovae. So these were type 1a supernovae are of few different types. This is type 1a supernovae. We can talk about the types later on, which are known to be standard candles. That is, they have nearly identical absolute magnitudes. Although they were able to place tight constraints on... Yes, there's a kitty here. Although we were... Here, you can look at him. better like that. Although they were able to place tight constraints on dark energy using the many supernovae that they detected, we can get a feel for the measurement by simply considering two of these. Consider then supernova 1997 AP, found at redshift 0.83 with apparent magnitude of 24.32, and supernova 1992P, found at low redshift 0.026 with apparent magnitude of around 16.08. Since the absolute magnitudes of these are the same, don't ask me how, because, oh, I see, they're doing a, the difference in apparent magnitude, oh, I see, the absolute magnitudes are the same, but the apparent magnitudes are different. Since the absolute magnitudes of these are the same, the difference in apparent magnitude is due solely to the difference in luminosity distance. So basically, absolute magnitude should be the same when you're comparing these things, but apparent magnitude is because of the luminosity distance, if it's getting farther apart because of something expanding the universe, for example, you know. The nearby luminosity distance is independent of cosmology, simply equal to some equation. Therefore, the only unknown remaining is fixed by the observations to be around 1.16. In a flat, matter-dominated, oh, thank you, MC24, how are you? In a flat matter-dominated universe of where the omega of the matter is 1, the luminosity distance out to z equals 0.83, so that's the redshift, is equal to 0.95, h naught to the minus 1, whereas a universe with matter of 0.3, so the omega is now 0.3, and a cosmological constant of 0.7 has a luminosity distance of 1.23 h naught to the minus 1. Wow. So 0.95 versus 1.23. The apparent magnitude of this single distant supernova then suggests that dark energy pervades the universe. So basically, if you put in just the matter density, which would be, you know, if everything was matter density, then you could just give it the number 1. If matter density is only 30%, you could give it the number 0.3. But if you're giving matter density the number 0.3, then cosmological constant is 0.7. So, luminosity distance will be different based on what numbers you give those, and the apparent magnitude of this single distant supernova then suggests that dark energy pervades the universe, because that's the more correct one. Of course, the discussion of the previous paragraph does not account for uncertainties. Typical uncertainties in the magnitudes are of order 0.2, nor does it do a careful fit to all known supernovae, allow for extinction by dust, or allow for the variation of the absolute magnitude correlated with the duration. The supernova groups did all of those things and emerged with the constraints shown here. There is a constraint picture here. The two free cosmological parameters are the matter density and a cosmological constant. So they can these are two parameters in this discussion, and they can vary those. Something we now recognize as one possible form of dark energy, one in which the energy density is constant. So if we are going with the cosmological constant way of looking at dark energy, where the energy density is constant, much like it was historically introduced, then that's one possible form of it. If it's changing, well, that's probably the more likely, but, we can consider it as a constant as well. Note that the theorists' dream universe, flat and matter-dominated, which is the omega would be 1 then, is excluded with high confidence. So from this whole thing, from this whole discussion and observation and trying out the different parameters of omega m and omega lambda, where omega lambda is the cosmological constant or dark energy thing, which being a constant is one iteration of it. So the theorist's dream was a universe which is flat and matter dominated, because then they would be like, okay, we get it. It's matter dominated now. It used to be radiation dominated in the past, and then things were like this. Now things are like this. Things have developed more. The universe cooled down, made stars and galaxies, all that stuff, structure, all that stuff. And, of course, it's not really perfect, because even within the matter density, there is a large fraction of it that we don't understand because of dark matter. And we call it dark matter because we don't understand it. But, let's say that if rho m is 1, then the universe would be flat and matter dominated. But that particular case is actually excluded at this point with a high confidence. Even a pure open universe where the matter density is 0.3 and the dark energy density is 0 is strongly disfavored by the supernova data. So we considered this two supernova case. They actually had a bunch of data with a lot of supernovae, and they did this math for that luminosity distance thing we were discussing to see if the luminosity distance is changing or not, which would basically, this sentence right here, objects of fixed intrinsic brightness. If the intrinsic brightness is the same for certain objects, but they appear fainter at different redshifts, then what that means is the universe is composed of dark energy, because it's getting expanded out, and the distances are getting larger because of something else. This something else is the dark energy. So while highly popular, figure 2.7, this is the figure right here. It has no Big Bang. Then it has, look at this figure. Look at the no Big Bang is right here. 68%, 90%, 95%, 99%, where this is the cosmological constant and this is the matter density. Right here is flat. Flat would mean that this is 0. This is expands forever, recollapses eventually, closed, flat, open. That's what this is. So it allows for too much freedom in one sector and too little in another. Most of the region in the figure is taken up by a universe with both dark energy and non-zero curvature. So that's not flat. So although one or the other of these has been argued for, seldom have cosmologists suggested that the universe contains both. Thus, except for the flat line and the omega lambda equal to 0 line, most of the region is at least aesthetically unappealing. The figure allows for too much freedom. So as in, all these possibilities are kind of allowed. On the other hand, the only form of dark energy budgeted for is the cosmological constant to open up other possibilities. So basically, the cosmological constant is one iteration. You could have others. You could have all of these. We could consider this other way. Equation 2.55. Where is equation 2.55? This is where partial rho, partial t that's not a very nice form of this equation, but conservation law can be applied immediately to glean information. Matter has effectively 0. Oh, conservation law in an expanding universe. That's what that equation is. Okay. The only way for this equation to be satisfied with constant energy density is if the pressure is equal to minus rho, small rho. One might imagine energy with a slightly different pressure and therefore energy evolution. a cosmological constant corresponding to omega, small omega of -1, matter to 0, and radiation to 1/3. With this new freedom, let's see what the supernova data imply for the equation of the state of the dark energy if we fix the universe to be flat. So that's what these new curves are telling us. Shows that the value of little omega greater than around -0.5 are disfavored. A cosmological constant is consistent with the data, but it is by no means the only possibility. So once we do all that, this expression agrees with our knowledge of the cases explicated above of omega of 1/3, 0, and -1. So there is some other, see, omega here is in the y-axis. So there's some other possibilities considered here, equation of state versus the density, matter density. The epoch, so basically this cosmological constant nomenclature is probably going to be misleading now because we're allowing for the energy density of dark energy to probably change, basically. The epoch at which the energy density, so the universe has gone through evolutions. Sometimes people call these epochs, E-P-O-C-H. The epoch at which the energy density in matter equals that in radiation is called matter-radiation equality. So the epoch at which the energy density in matter equals that in radiation is called the matter-radiation equality. Because remember, in the beginning, radiation was more dominant. At some point, matter became more dominant. So probably at some point in between, they might have been equal. It has a special significance for the generation of large-scale structure and for the development of CMB anisotropies because perturbations grow at different rates in the two different eras. So before this equality versus after this equality, it is therefore a useful exercise to calculate the epoch of matter-radiation equality. To do this, we need to compute the energy density of both matter and radiation. Energy density of both, yes, of course. And then find the value of the scale factor at which they were equal. Yes! Oh my gosh! That's awesome. So total energy density in radiation is this right here. To calculate the epoch of matter-radiation equality, we can equate these things and we can get the scale factor at which this happened. And a different way of expressing that is to give you the redshift at which this happened. So the redshift of equality, matter-radiation equality, is around 2.4 times 10 to the 4 big omega matter h squared. Note that obviously as the amount of matter in the universe today goes up, the redshift of equality also goes up. For our purposes, it will be very important that the redshift of equality is at least several times larger than the redshift when photons decouple from matter. So around z star of like 10 to the cubed. Thus, we expect photons to decouple when the universe is already well into the matter-dominated era. Wow. Okay, now we will talk about Friedman, Robertson, Walker. Somebody asked about this before. So this is in the summary. We will talk about this now. The smooth universe can be described with the Friedman, Robertson, Walker metric, which implies that physical distances are related to coordinate or co-moving distances with the time-dependent scale factor A of t. So this is small a of small t. T is cosmic time. The time dependence of the metric is determined by the Einstein equations. The time component of the Einstein equations reduces to something in a flat universe. Measuring distances in the expanding universe is tricky, but all relevant distances can be obtained from the co-moving distance between us and a source at a redshift of z with This expression right here, another important distance is that light could have traveled since t equal to 0. This is usually expressed as a time, the conformal time. The conformal time will be the natural time variable when we come to consider the evolution of perturbations in the universe. So photons in the universe have a Bose-Einstein distribution. So we know this because photons are bosons with zero chemical potential. So their energy density can be determined by measuring their temperature, which is nice because we have a way to measure that. Neutrinos have a Fermi-Dirac distribution, also probably with zero chemical potential, but there is some ambiguity in their energy density because of our ignorance of the neutrino masses. Early on, this ambiguity is irrelevant since the temperatures are so much larger than the masses and neutrinos behave relativistically. Thus, the uncertainty in neutrino mass does not affect Big Bang nucleosynthesis at temperatures of order 1 MeV, and probably not even the epoch of matter radiation equality at temperatures of order 1 eV. Wow, the neutrino temperature is a factor of 4 over 11 to the 1/3. Remember, we saw this smaller than the photon temperature. This and the difference in statistics implies that a species of massless neutrinos has an energy density equal to 0.23 times that of photons. A single neutrino generation with mass of mu contributes around 0.01 of the big omega neutrino. In addition to photons and neutrinos, the universe consists of baryons, best determined by nucleosynthesis to have been around 0.0205. Dark matter is 0.3 and dark energy is 0.7, a new form of energy with negative pressure. There is significantly more energy today in non-relativistic matter than in radiation. However, since the energy density of radiation scales as a to the minus fourth, while that of matter as a to the minus 3, the very early universe was radiation dominated. The epoch at which the matter density was equal to the radiation density delineates these two regimes at a certain scale factor, which is given by 4.15 times 10 to the minus 5 divided by omega mh squared, where that's Hubble constant. So all of this kind of teaches us a lot about the various bookkeepings and accounts of the universe. We talked about cosmic inventory today, including some specifics about the numbers, literally, of these cosmic components. We covered photons, which really dominated the universe in the beginning parts of it in time. Then we talked about baryonic matter density, which is basically the protons, neutrons, and electrons. We also talked about matter density in general, which comes from a gravitational point of view, which also gave us dark matter, because we found that there is a bunch of matter density fraction which is not accounted for by the baryonic density. We also talked about neutrino as a component and contributing to the energy density. And then lastly, we talked about dark energy. And we saw that you basically had to fit. You could start with the cosmological constant, give it something, some fraction as a component, and then see how it fits with what we know and whether it is supporting the observation data or not. And we got a direct evidence of dark energy because we were able to look at the supernova data. We collected a lot of data, including supernovae. I'll read this part to you again because this is important. Two groups observing supernovae reported direct evidence for dark energy. The evidence is based on the difference between the luminosity distance in a universe dominated by dark matter and one dominated by dark energy. So you could say that the universe is all dark matter, because ordinary matter is much less, basically, and see what you come up with and see if it fits that model of the luminosity distance between these objects or not. Because basically, if dark energy is really a thing, then the luminosity distance is larger for objects at high redshifts in a dark energy dominated universe. Therefore, objects of fixed intrinsic brightness will appear fainter if the universe is composed of dark energy. So they had to get some supernovae samples at these various redshifts that have the same intrinsic brightness, but have a different apparent brightness. I think they call it apparent magnitude of the luminosity, basically. And they have to then see if that apparent magnitude is changing or not, and what it comes out to be versus what it would come out to be if it was not dark energy dominated versus what they actually see. And they see that it is, you need the dark energy. And then they found that when you consider dark energy to be just a cosmological constant, that might be kind of only part of the picture, and you might need more variability. And they gave us this picture, which is equation of state, little omega versus matter density. Constraints in a flat universe from type 1a supernovae on the matter density. Basically, you can get these constraints in a flat. So considering if the universe is flat, then constraints on that from type 1a supernovae, as in many of the supernova data, on the matter density and equation of state of the dark energy. Cosmological constant corresponds to W or omega, small omega equal to -1, and matter to omega equal to 0. So basically, you might need a graph like this, which would allow for more variability. It's like a function. Basically, the equation of state of little omega as a function of matter density might actually be needed. The values of omega greater than -0.5 are disfavored. Wow. So a cosmological constant is consistent with the data, but it is by no means the only possibility. If omega is constant, this expression agrees with our knowledge of the cases explicated above. So this whole thing culminated into the requirement for needing dark energy, and how much of it. Well, we will go over this again because this stuff was a little bit complicated. We will definitely go over this again in another live stream as well. So not to worry. I'm trying to see if there is another better sentence to read again. Dark energy. So at this time, dark energy is 0.7 as far as the energy density of it goes. It's a new form of energy with negative pressure. Wow. Wow. And we don't know exactly what it is. But that's what we're finding. This is sort of by doing the cosmic inventory way of figuring out what the different components of the universe are. We need this thing called dark energy, and it is consistent with our observations of those supernovae data, which tell us that the universe is expanding. This was actually a very important discovery, and I believe it actually received a Nobel Prize as well. So if you want to look that up, I believe it was in the late 1980s time frame that they did that. Let me get the exact year for you here. It was, oh, maybe it was 1998 actually. I think 1989, there was something important, and then this particular study was from 1998 and 1999. So it's been some time since this was done, and it basically showed us that the expansion of the universe was happening, and it was even accelerating, and it's considered to be the direct evidence for dark energy, because there's got to be something that's doing that, and whatever that is, and gives us this another like component of the universe, this quintessential component, the fifth component. Okay, so that's where we will pick up and continue from next time. I'll chat for a few minutes here now. So now we just covered cosmic inventory. Thank you for being here. Next time we will summarize cosmic inventory, and the next topic is beyond equilibrium. Oh wow. Oh. You know what? Yes, that's right. You know, we didn't really talk about cold dark matter yet, but we will. Indeed, we will. So we know that the cosmological candidate for dark matter is called cold dark matter. Trying to find where exactly it's first mentioned. Baji. Look at all my markings from when I was a student for this. Ooh, yes, indeed. I think soon when we talk about Boltzmann Compton scattering, who cares? Not as interested in the... When we talk about Boltzmann equations, the nice thing is that the universe is basically these 5 things: photons, baryons, dark matter, neutrinos, and dark energy. Well, we don't really know what dark matter is. We don't really know what dark energy is, but we do know the other things pretty well, and we have all these equations for them. So we can deduce a lot about the other 2, or try to, because of that. And photons and things like that are really well understood. So, at some point we'll talk about, for example, Boltzmann equations. And it's going to be a lot of fun. It's going to be like stuff you've already seen in something like thermodynamics, quantum mechanics, etc., etc. Because this is stuff we kind of do and love. It's fine. It's the same in terms of cosmology. It's not like photons are, anything too different. So Compton scattering, stuff like that. Not boring stuff. So we will have some boring stuff. And then basically, the nice thing is that people try to describe cold dark matter, something like a theory or a candidate for dark matter that they call cold dark matter. They can try to do similar things with it, similar math with it, and see where we land and see if that is sort of viable, Like they've done, for example, Boltzmann equation for cold dark matter as a treatment of dark matter, So we'll see. We will see what we get from that. Boltzmann equation for baryons. Sure. So we will see where that takes us. Then we have Einstein equations. Perturbed Ricci tensor and scalar. Got it. Okay. Whatever. All right. Decomposition. Ricci, the Ricci curvature is initial conditions. Aww. Early times. Einstein-Boltzmann equations at early times. How nice. Initial conditions, like when the universe was a baby. Inflation of the universe, not of money. Inflation, Hubble volume. Got it. Hubble radius. Radiation domination. Basically, we will review. It'll come back up about the universe's evolution. So even if you forget, we will remind you as we keep going here. Scalar perturbations. Fine. So at some point here, we will get into inhomogeneities. Yay. Having set up the system of equations to be solved in the initial conditions for the perturbation, we can now calculate the inhomogeneities and anisotropies. Yes, finally, we will talk about inhomogeneities and anisotropies of the universe, because why not? Gravitational instability, mass near an overdense region is attracted to the center by gravity but repelled by pressure. If the region is... So negative pressure, remember, for dark energy, basically, it makes the universe expand. So it's almost like it's pressure, but in the other direction. If the region is dense enough, gravity wins, and the overdensity grows with time. So gravity goes like that, and pressure goes the other way. Look at that. So we just don't know what it is, but it's got negative pressure. Dark energy. Yay. So not too bad. Honestly, dark energy is... Some people think of it as a less... Oh my God, I got so scared when I saw the coat over there in my video here. I'm like, who the frick is that? It's just my coat. Okay, all right. Thank God. I get scared by my coat sometimes. Some people regard dark energy as a not as mysterious topic. Because... I don't know, because of what I just said. But dark matter, on the other hand, it's matter. It interacts with gravity, but we don't know what it is. That's sometimes a more concerning topic for people beyond cold dark matter. So Cold dark matter is not the only candidate for dark matter. We will also talk about beyond cold dark matter. But first, we will talk about cold dark matter. So don't worry about that. Then what else? What else? What else? I'm just like flipping through and seeing what else is there here. Anisotropies, more anisotropies. Oh my gosh, Scott, get to the point already. This is a textbook, I get it. But Scott Dodelson, can you please get to the point of what you want with these anisotropies? Okay, fine, all right. Did they not give you enough to do it for me, lab? You're writing a whole book on this? Acoustic acoustic oscillations. Tightly coupled limit of the Boltzmann equations. Oh yeah, I remember this. Acoustic oscillations. God, kind of hate these actually. To be totally honest, photon diffusion. Oh. This is reminding me of my second year of grad school. Okay, all right. It was a tough time. Fine. Sash-Wolf effect. Okay. Hi, Baji Babu. Hi. Okay. Lesson is done because Baji's sitting on the book now. So we will pick up a cosmic inventory. We will summarize it tomorrow again. I realize that the topic is a little bit complicated, so we will summarize it in a more succinct and good-like manner again. In general, I summarize things anyways when I first start the topic and when I first start the live. So there's usually a good amount of summarizing. So I'll do that again next time. And then I'll continue on to continuing with more of cosmology or something else. We'll see. I think it'll properly introduce, of course, all the different components of the universe, all the 5 different components. And so that'll be good. And we'll take it from there. That's right. I wanted to talk about cold dark matter, so it'll be good. I'll introduce all the cosmic inventory stuff again, and then I'll talk about this cosmological perspective on dark matter candidate, which is cold dark matter. So we'll talk about that. It's not really something I have read about outside of cosmology, so I think we'll pretty much... Hi, Booba. Come, Baba. Baji wants to be on lap. Come, Baji. Sit. It's okay. Sit down. So that's why, this will be good. We'll talk about cold dark matter. In this context, it'll help. And then we will move on to other things. And we will get a little bit more on maybe dark energy, because dark energy is just, well, it's not anything just, but basically it's, when we consider it again in terms of anti-gravity, I think it'll bring sort of that perspective that might be helpful. Hi, Baji Bambu. I know I'm holding this mug. That's why I can't pet you yet. 1 second, Baji. So we will get the cold dark matter standpoint, and then more about dark energy as well. All of your stream. Your voice is way too soothing. Your comments are wild, but I gotta be at the office tomorrow. It's bedtime. Have a good night. Thank you again, Dora Dora. If you're seeing this, or if you're listening to the video as a video upload later on, we finished up the discussion on cosmic inventory. So hopefully you catch the whole video later on, maybe when you're working like a podcast episode or something. And then join us again tomorrow We will continue the discussion then. I play this while I'm drinking and driving. Okay. When I commit crimes. Okay. Boston, definitely in the Irish Mafia. Oh, a kitty looks like my cat. Everybody, thank you so much for joining. Could somebody like the live so that I can get 10 likes, please? That would be amazing, and very much appreciate all of your support and chat and comments and activities here on the live stream. Thank you so much for being here. Thank you for joining, and see you next time. And also, if you're watching this as a video upload later on, please leave your comments. Love to read them when I look at the channel later on. And yeah, Heike, let me know your comments on the cosmic inventory. And Reese, if you're seeing this, where have you been? And also let me know about your comments on the cosmic inventory, and we'll try to catch up really soon here. So thank you, thank you, thank you, thank you. Love all the discussion, and we will see you next time. Thank you so much. Hello. I'm just about to sign off, but thank you so much for joining. But yeah, see you next time. We will continue with the cosmic inventory thing. What else? Who else? I was gonna say something else. Ooh, I haven't seen I think it was Callie, somebody called Callie, who had joined once and they liked the physics. If you see this video, leave me a comment. That would be really amazing. Yeah. We just finished a discussion on cosmic inventory. Ooh, I'll leave you with this, actually. There's a very nice picture for you to look at right here. This is the dark energy states as a function of the matter density. You can take a look at that. And we will have a quiz on this the next time. I'm just kidding. We will have more fun discussing this stuff next time. Really appreciate all your support, everybody. Keep watching our videos and shorts and come to our live streams. Really love it when you participate, and have a good night.